Hey everyone, since I am not going to be there today, I thought it would be a good idea for you guys to at least have access to some sample problems from your Q4 midterm review packet, which by the way is your final for trig. So I'm going to go ahead and do one from each section, and hopefully you guys will be able to keep up in your notes. So I'm going to start off from the first section here. I'm just going to do number 2. The problem reads sine of 15 degrees. Well, in order to find sine of 15 degrees, I'm going to have to employ a sum and difference formula. So what I want to do is I want to use sine of two angles that I readily know the answers for. And, given the fact that we're in degrees, I figured 45 minus 30 would be the best option because I do know sine 45 and I do know sine 30. And so I'm just going to go and expand this using sum and difference for sine. So that becomes sine 45 cos 30. I'm subtracting on the inside, so I'll be subtracting on the outside, sine of 30 cos of 45. And then from here, I just evaluate what each of these things are. Sine of 45 is 1 over rad 2, but again, for these problems, I like to keep it a little cleaner. I'll use rad 2 over 2. Cosine of 30 is rad 3 over 2 minus sine 30 is 1/2 times cos 45. Again, I'll use the rad 2 over 2 version. Well, from here, my left side becomes rad 6 over 4, just multiply the top and bottoms together, minus rad 2 over 4. And at this point, you can pretty much close out the problem. Now, some people might be a little more ambitious, and they may just combine the two numerators over one denominator. It doesn't matter which one you present to me. I'll take either one. Okay? So that's from the first section. So that's how you generally do each problem in the first section. Number 12. From the second section, again, sum and difference formula. So what I've got is I've got cosine of 13 pi over 15, cosine of negative pi over 5, and then I'm subtracting sine of 13 pi over 15, and then sine of negative pi over 5. Okay? So, again, I'm working backwards here, so this looks like, since my pattern's going cosine, cosine, sine, sine, that means that I'm using sum and difference for cosine. And it looks like the two angles in question here are 13 pi over 15 and negative pi over 5. And I'm going to be adding these things together because they were being subtracted on the outside. Okay? So, what does this ultimately look like? It looks like cosine of 13 pi over 15 plus a negative is minus. Now remember, I also want to get a common denominator here. So it looks like this is going to be, if I multiply the top and bottom by 3, then I get 3 pi over 15. Well, what does that give me? It gives me cosine of 10 pi over 15, which is ultimately going to reduce out. Looks like I can divide both by 5. So I get cosine of, looks like 2 pi over 15 divided by 5 is 3, which ultimately gives me negative 1/2 as the answer. Okay, cool. So let's go ahead and keep moving. Now in the next section, number 17, we're actually using sum and difference formula in a little bit of a different way. I'm combining two of the ideas here. We're going to use sum and difference formula to prove certain identities. And so the idea behind this is you want to go ahead and tackle this exactly like you would a trig identity. So how do you do that? Well, remember, the first thing you want to do is you want to tackle the side that gives you more stuff to work with. So clearly that's our left side. We can go ahead and expand each of these individually. So I know that cosine of x plus pi over 6 will expand out into a cos, sine, sine. And it's going to be subtracted because I'm adding on the inside. Well, what serves as the piece that plays the x role? Well, that's x unimaginatively. The portion that forms the y role is going to be this pi over 6. So what does that look like expanded? It looks like this. Cos x, cos pi over 6, minus, right, because I'm adding in the middle, so I'm going to subtract on the outside, sine x, sine pi over 6. Okay, so that's what this first portion became. Now I'm going to add sine sum and difference. So that's going to be sine x, not sine, sorry, cosine pi over 3 minus cosine x sine of pi over 3. And remember, all of this will hopefully end up equaling 0. So let's see if that's true. Cosine of pi over 6 is rad 3 over 2, and I get that being multiplied by a cos x. So this portion is now gone. Minus sine of pi over 6 is 1/2 sine x. So now this portion is gone. Plus cosine of pi over 3 is 1/2 sine x. And some of you guys might be able to start seeing where this is going. Minus sine of pi over 3 is rad 3 over 2 cos x. And don't forget, all that equals 0. Well, let's see what happens here. I got a negative 1/2 sine x. I got a positive 1/2 sine x. Those guys can effectively knock each other away. Rad 3 over 2 positive of cosine and a rad 3 over 2 that's negative cosine. Those effectively go away. I end up getting 0 equals 0, and that's how you do this identity. Okay, cool. Let's keep moving. All right, number 23 says find sine 2x and cos 2x from the given information. So now we're moving forward. We're using double angle now. Now this is one of the more complicated ones. Cosecant of x is equal to 4, and the only thing they give to us is that tan x is less than 0. So this is the first time that we're given a problem that looks like this in this particular section. So how do we use this information? Well, unlike numbers 21, 22, and 24, where they explicitly tell you which quadrant your angle is in, this time you have to extrapolate the information based on the implication. Well, here's the thing, is that I know that cosecant is 4 over 1, which means that my 4 is my hypotenuse and my 1 is my opposite side, right? Because cosecant is reciprocal of sine, right? Okay, well here's the thing, is that when they're telling me that tangent of x is less than 0, what they mean is tan x produces a negative value, because all numbers that are smaller than 0 are negative. And so what does this mean? How can we use this information? Well, I know this much. I know that sine is positive, and I know that tangent is negative. There's only one place on the entire unit circle that allows for sine to be positive and for tangent to be negative, and that is in quadrant 2. Okay, so hopefully that logic kind of made sense to you. From here, I'm going to go ahead and draw my quadrant 2 triangle with x being my angle here. I know that my hypotenuse is 4 and my opposite side is 1. In order to figure out what this side is here, I'm going to go 16 squared minus 1 squared, so it's rad 15. But I'm going to go ahead and make sure that I remember that that's negative because I'm in quadrant 2. So what does sine 2x look like? Well, before I figure that out, I know that sine 2x is 2 sine x cos x. And here's what I know. I know that because cosecant x is 4, I know that sine x is equal to 1/4. I also know, based on the Pythagorean theorem here, that cos x is equal to negative root 15 over 4. So now I just kind of punch those things into here, so I end up with 2 1/4, because that is what replaces the sine x, and my cos x is going to get replaced by a rad 15 over 4. At this point, these guys knock each other out. You end up with a 2 down here. 2 times 4 is 8, negative rad 15 over 8 becomes the answer. Cos 2x is going to use cosine double angle. So I know that that's cos squared x minus sine squared x. Well, again, I already know what these things are. So I can use that information and say that it's two values being squared being subtracted. So I've got negative rad 15 over 4 inside, and then I've got 1 over 4 inside. Negative rad 15 over 4 will emerge positive if I square it, so ultimately the rad and the squared are going to knock each other out, giving me 15. 4 squared is 16 minus 1 over 16, which is going to be 14 over 16, which is, if I reduce that, divide both portions by 2, 7/8. And that's how you do the problems from 21 through 25. Again, I'm trying to choose some of the more complicated ones. That way, hopefully, when you look back at some of the simpler ones, they appear simple. Okay, let's take a look. It seems like number 34 is next. So number 34, again, I'm actually going to do two from this section, one simple, one not so simple. Sine inverse of negative rad 2 over 2 or negative 1 over rad 2. I'll go and write it like that just to show you that that option exists. So again, here's what I'm looking for. I'm looking for the straight up sine inverse of negative 1 over rad 2. So remember, sine inverse can only pull values from the first quadrant and the fourth quadrant, or quadrant negative 1, right? That's what we call it, because the range of sine inverse is from negative pi over 2 to pi over 2. This value here is negative, which means I am pulling my answer, my angle, from quadrant negative 1. So what I have to think about is what angle in quadrant negative 1 produces this value of negative rad 2 over 2 or negative 1 over rad 2 for sine. Well, there's only one angle that can do that. It's negative pi over 4. Okay? That's one of the more simple ones. When we start getting into compound ones, sorry, not 35, 45. When we start getting into the more compound ones, it starts to get a little more complicated. So I've got tangent of tan inverse of 5. Well, technically it's 5 over 1, right? And normally we would, disqualify that if we saw some kind of inverse function being something greater than 1. It's just not possible until we remember that tan inverse has a domain of all real numbers, so we're actually okay on taking tan inverse of 5. But because tan inverse of 5 isn't readily known on the unit circle, what we have to do is instead we just draw a triangle of this thing, with this being my theta, or my x. Tangent is opposite over adjacent. And so what I'm going to do is I'm going to add these guys together after squaring them and make that my hypotenuse. And actually, I really don't need this. I'll just go ahead and do it after looking at my outer function. I actually don't need it. But 25 plus 1 is 26. But again, I'm not going to need that information because I'm going to take and end up taking tangent of that angle, which gives me opposite over adjacent. It's really just 5. Okay? So that's how you do number 45 so far. Let me go and turn the page real quick. I'll be right back after I get the other page. Okay, and we're back. So here is the next problem from the next section. We are being asked to write the equation for this both in terms of sine and cosine. And so hopefully you guys remember there are a few things that you should probably look for. The first thing you want to look for is that vertical shift. That's going to be your anchor on this problem here. So the vertical shift, and actually I think I'm going to move this up here. The vertical shift is going to be positive 2, right? Because my black line is there. From there, from getting the vertical shift, we can pretty much determine the amplitude. Looks like this thing is going all the way up to 6 and all the way down to negative 2, which leads me to believe that the amplitude is 4. 4 up, 4 down. And then next thing we're going to do is we're going to go ahead and grab the period of this function. Now the period of this function, remember, there are 3 ways to find period. Peak to peak distance, valley to valley distance, or peak to valley distance times 2. The most obvious one in this particular problem is actually peak to peak distance, because here's what I have. I have one peak here and one peak here. So it looks like I can go ahead and go peak to peak distance here. The distance between 5 pi over 12 and negative pi over 12 is 6 pi over 12, or pi over 2. Now, before we get too ambitious, the period itself doesn't exactly help me unless I use it to find the frequency. Now, frequency is found by taking the original period of the function, in this case being sine or cosine 2 pi, divided by the period found. So, to take this original period and divide it by the period found will get me the number 4. Okay? So, here we go. From here, I can go ahead and do a shell of each function. So I've got y equals 4 sine for x something plus 2. And I can go ahead and do y equals 4 cos 4 times x something plus 2. Again, the only thing that's going to determine the difference between a sine or a cosine graph is where this graph is being phase shifted. Okay? So, the most obvious one is a cosine graph. Cosine looks like it could originate here, here, or here, because cosine starts at the high point and goes low. Now, I'm going to go ahead and go with my plus pi over 12 option for this one. Again, you could go minus 5 pi over 2, or you could go minus pi over 6. Now keep in mind that if you do minus pi over 6, you would have to make cosine negative because it started at the low and go high. Alright, so now let's take a look at sine. Sine looks like it would start either here or here. It doesn't matter which one you choose. I'm going to go ahead and choose this guy because I feel like having a negative sign. Again, you could go positive sign if you wanted to have your point here, but I'm arbitrarily choosing this point that I drew the arrow towards. So, what does this look like? Since I don't have an exact value right here, I don't know where that is. I have to find out where that is. Well, that position right there is going to be halfway between this peak right here and this valley down here. So what I'm going to do is I'm going to average them out. So what I've got is pi over 6 plus negative pi over 12, and then I'm going to multiply those coordinates by 1/2. So the first thing I'm going to do on the inside is I'm going to find a common denominator. Well, that's 2 pi over 12 minus pi over 12 times 1/2. Well, that's going to give me pi over 12 times 1/2, which will give me pi over 24. Now, since I'm shifting this graph to the right this time, that's going to end up becoming minus. Now, remember, I chose the point that will give me a negative value of sine because sine is now upside down. So I got to make sure that if I'm going to be stubborn and choose this pi over 24 x coordinate, I want to make sure I flip my sign upside down. Okay? Let's move on to the next problem. Oops, looks like it's a sinusoidal app. I'm going to go and copy and paste the problem. I'll be right back. Okay, so it looks like 65 is the problem of choice here. Researchers find a creature from an alien planet. Its body temperature varies sinusoidally with time. 35 minutes after they start timing, it reaches a high of 120 degrees Fahrenheit. 20 minutes after that, it reaches its low of 104 degrees Fahrenheit. Sketch a graph, write an equation, what was the temperature when they first started timing. Okay, we've been through problems like this before. First thing to note on this problem is that despite the fact that it appears that we are working in degrees, these degrees are not angular degrees. These are temperature degrees. So please do not think that we're working in degrees in this problem. We're still working in radians. These degrees signify its body temperature, not the angle of its body temperature, if that even makes any sense. So we're going to first off sketch a graph of this problem here. And so I'll go ahead and just draw this graph real quick. It looks like the first known time that I'm being given is this 35 right here. So 35 can safely go there. And at that point in time, the alien's body temperature was 120 degrees Fahrenheit. And they said 20 minutes after that, it reaches its low of 104. So I know that at time equals 55, I'm at my 104. Now, if I wanted to draw a third point, and I do want you to draw that third point, it would be up here because we assume that the body temperature varies sinusoidally with time. Alright, so I do want you guys to draw that third point for no other reason other than the fact that it shows that convincing work, but also it really gives you this really clear idea of what exactly, which trig function it is you're dealing with. Because at this point, the problem should be pretty obvious. Now, if the first high point is at 35, and the low point is at 55, it stands to reason that if this alien's body temperature varies sinusoidally with time, that the next logical time period at which the body temperature is going to be at 120 is 20 minutes after this 55, or 75 minutes. Okay? So we just sketched a graph, and now we need to do part B, write an equation expressing the temperature in terms of minutes. So I know that I have y equals, well, first thing I want to do, just like the last problem, is find that vertical shift. Well, I'm not being given a direct vertical shift like the last problem, so how do I do this? Well, I'm going to average these two values, 120 plus 104. Well, that gives me 224, and I average them by dividing by 2, giving me 112. So that's how I'm going to be able to tell what my vertical shift is. It's 112. From 112, it looks like I move 8 up and 8 down. So that looks like that's my amplitude. Quite clearly, this graph is cosine. Now, it could be sine. You really could make it sine if you really wanted to look for those two intersection points, but I'm all about keeping this problem pretty simple. You're not being asked to write both. You're being asked to write an equation, not both equations. So go with the most convenient one. It's cosine, most conveniently. From here, the period looks like it's about 40 minutes. Actually, not even about 40 minutes. It is exactly 40 minutes. So if my period is 40 minutes, then that means that my frequency from the last problem is 2 pi over 40. In other words, pi over 20. So that's going to go in here. And now it's just t minus 35, because I'm phase shifted to the right by 35 minutes. So that's part B. Part C. What was its temperature when they first started timing? Well, when they first started timing, that means that time was 0. And now I just got to find out this value. So what's this value here? This is negative 35. Now be careful. It's negative 35 times the pi over 20. Now I can go ahead and slash these off because I can divide both of them by 5, giving me y equals 8 cosine. Well, 35 divided by 5 is 7, so negative 7 pi. And 20 divided by 5 is going to be the 4. Luckily, this is a value we know from the unit circle. Cosine of negative 7 pi over 4 places me in quadrant 1, right? Because negative 7 pi over 4 is rotating clockwise all the way to there, placing me in quadrant 1. So what I've got is, and I'm going to go ahead and use rad 2 over 2, and I think there's a very good reason why I'm using rad 2 over 2. It's because that can happen. So I get 4 rad 2 plus 112 degrees Fahrenheit was the alien's temperature at time equals 0, or when they first started timing. Now, notice how I cut parts D out of 64, 65, and 67. We haven't quite gotten that far yet. So one day I will show you guys how to do it. It's just not right now. So that's number 65. Let me go and find the next problem real quick. Okay, let's go ahead and delete this stuff here. Okay, so it looks like I'm going to do number 71 next. So if you guys haven't noticed, and I asked our substitute teacher to relay this message to you, I am cutting parts A and C out of these instructions. So you are only solving these in radians, okay? So this problem here goes as follows. 2 sine squared x minus sine x equals 1. Hopefully at this point you'll realize that this is sine squared and sine. It's a quadratic, so I'm going to go ahead and subtract 1 from both sides. I get 2 sine squared x minus sine x minus 1 equals 0. I'm going to factor this thing. I get 2 sine x, sine x. The only numbers I can multiply to become 1 are 1 and 1. I'm trying to create a negative 1 in the middle, so it looks like I'm going to go minus on the right, plus on the left. So I am looking for where sine x equals negative 1/2 and sine x is equal to 1. Okay, so let's do part B first, which is solve between 0 and 2 pi. So one cycle of the unit circle looks like we're doing a restricted function in radians. So for part B, on the left side, it looks like where does sine x equal negative 1/2? Well, that happens when x is in quadrants 3 and 4. We're dealing with sine. So it looks like that's going to be 7 pi over 6 and 11 pi over 6. Part C, is going to be when x is, oh, I'm sorry, I missed out on sine x equaling 1. The other portion of my answer is going to be when x is equal to pi over 2. Part C, I'm going to go and use these values again, except now it's going to be 7 pi over 6 and 11 pi over 6 and then pi over 2. And I structured these a little bit differently than my top answer here, because now that I'm going for all radians in part D, actually not part C, I'm now moving towards an unrestricted cycle of the unit circle, which means every iteration of 7 pi over 6 can be an answer in the positive spin direction or the negative spin direction. Same thing goes for 11 pi over 6, same thing goes for pi over 2. And don't forget that when this happens, I need to include the statement where n is equal to 0, 1, 2, ... Okay? So that is it for 71. Let me go ahead and get the next problem ready. Okay, number 83. 83 reads as follows. Solve for the requested trig function. You are given this information, cos theta equaling 4 over 7, and they tell you that theta is in between 90 and 180. So again, oh, and then I'm sorry, we're being asked to find tangent of theta. Okay, so how do we do this? Well, this information here tells me something. If theta, my angle, is in between 90 and 180, then what I get is I'm in quadrant 2. Now, initially, this problem actually didn't make any sense. It's because I didn't copy it down correctly. Cosine is negative 4 over 7. Now the problem makes a little bit of sense. If I'm in quadrant 2, cosine's negative, which means that this problem should now hold up to scrutiny. So now I'm going to go ahead and draw my quadrant 2 triangle with cosine being adjacent over hypotenuse, and don't forget this 4 is negative. So now I have to go ahead and find out this third side because I have to find out tangent of theta. Well, how do I find out this third side here? Well, this third side here is going to be found by the Pythagorean theorem. So I've got x squared plus negative 4 squared is equal to 7 squared. So what do I have? I have x squared plus 16 equals 49. So x squared equals 49 minus 16. So it looks like I'm looking at a 3 down here and a 3 right here. So rad 33 is what I'm looking for. And don't forget, this is the angle in question. Now I just have to find tangent of that angle. So tangent of that angle is going to be opposite over adjacent, so negative root 33 over 4. And there you have it. Okay, let me go ahead and get the next graph ready. I will pause for a second. Alright, let's go ahead and take a look at one of the rational graphs. I'm going to go ahead and select number 86 to do. It reads f of x is equal to x minus 4 over x minus 1 times x plus 2. Okay, so it has been a little while since we've had to look at a rational graph, but hopefully these steps will make sense. I'm dealing with something rational, which means that there is room for error. Because I have variables on the bottom, I could end up with potentially dividing by 0. How do I account for a divide by 0? I create vertical asymptotes, which tell me these are the numbers that are going to give me trouble. So it looks like the numbers x equals 1 and negative 2 are going to give me the trouble, because if x equaled either of those, I'd have a 0 on the bottom. Horizontal asymptotes deal with end behavior. So what I have here is I've got an x up top, but if I was to FOIL this out, which it theoretically could be done, I'd have an x squared on bottom. So what I have is a trillion, as x goes to infinity, a trillion, 10 trillion, 50 trillion, over 50 trillion squared. And basically, 50 trillion over 50 trillion squared is basically 0, because the 50 trillion squared will just eclipse the 50 trillion up top, even though they're both really huge numbers. Okay, cool. So now, if I go to my x-intercepts are found by setting the top thing equal to 0, so that's just going to be 4, 0. And then the y-intercept is found by setting or making x 0, so I know that I end up with a 0, comma, -4 over, looks like -2, so I'll go and clean that up a little bit. It's going to be 0, comma, 2. Okay, cool. So, no holes, by the way. No holes, because if there was a hole, I'd be able to cancel something out, so no holes. So, here we go. Let's go ahead and graph this thing. I'll go ahead and do that. Okay, cool. So what we've got here is we've got vertical asymptotes at 1 and -2. X equals -2, x equals 1. Got a horizontal asymptote at y equals 0. I have an x-intercept at 4, comma 0, which is right here. And I have a y-intercept at 0, comma 2, which is right here. Okay, so how's this thing going to actually pan out? Well, it's hard to tell. It could do a number of things. So, because I'm not too sure about how it's going to turn out, I'm probably going to use a sign chart on this one. My sign chart numbers are going to come from my vertical asymptotes, which is where my function is undefined, and my x-intercept, which is where my function equals 0. So it looks like my numbers will be -2, 1, and 4. So it looks like here I've got an x minus 4, x minus 1, x plus 2. Let's go ahead and see what this thing turns into being. X minus 4 won't hit its stride until -4, so anything before that's going to be negative and then positive here. X minus 1 will hit here, so I've got minus, minus, plus, plus. And then here I'm going to get minus, plus, plus, plus. So I've got minus, plus, minus, plus. Okay, so what that means is that I have a negative thing all the way until my asymptote. So it's going to shoot down like that. It's positive on the other side, so it's going to shoot up. And then it's going to hit this 1 right here, and it's going to stay positive. And 1 is my asymptote, so that means that this thing is going to actually emerge up like this. On the opposite side of 1, which is my asymptote, it's going to be shooting down because we're negative. And then here's the weird thing, is that notice how I have this x-intercept here at this 4, comma 0. That means that this graph is actually going to pass the horizontal asymptote, which is a rare thing, but it does happen, and it has to arc back down. And the reason it arcs back down is because the end behavior ultimately must pull this function back down towards that horizontal asymptote. So that is what number 86 is going to end up looking like. Okay? Let me go ahead and set up for the next problem real quick. I'll be right back. Okay, with number 91 here, we are moving backwards in time towards exponential equations. Now, remember, the first thing I always ask you guys when you have an exponential equation, and again, it's an exponential equation because we have a variable in the exponential area. So what's the first thing I always tend to ask you guys? Well, I always ask you, is there any possible way for the bases to be forced to be the same? Like, could I reduce this 4 to have a base of 3, or vice versa? It doesn't look like it, so when it doesn't look like it, I must resort to using a logarithm on both sides. So what I get out of this is I get the natural log of 4 raised to the x minus 1 equaling the natural log of 3. From here, I can use my exponential and logarithmic rules to kick down the x minus 1, and that's times the natural log of 4 equaling the natural log of 3. From here, I don't have anything terribly complex, so what I'm going to do, I'm going to change it up a little bit. I'm going to divide by the natural log of 4 on both sides, and what I get is x minus 1 equaling the natural log of 3 over the natural log of 4. From here, it's just a matter of getting x by itself, so what I get is x equaling natural log of 3 over the natural log of 4 plus 1 on the outside. And that is your calculator-ready answer. Okay, number 97. we are now simplifying logarithms. So you guys have actually seen this problem before. We're just kind of rehashing it. 1/2 times the natural log of 9 plus 1/3 times the natural log of 8. We're going to kick these in here but using my exponential rules and logarithmic rules. So what I get is I get the natural log of 9 to the 1/2 plus the natural log of 8 to the 1/3. Well, 9 to the 1/2 is the same thing as the square root of 9, so that's the natural log of 3, plus the natural log of 8 to the 1/3 is the same thing as the cube root of 8. That becomes a 2. And from here, two logarithms of the same base being added together means that the answer portions are being multiplied. So you ultimately end up with the natural log of 6. I'll clean this up here. Feel free to pause anytime you want to if you feel like you need to spend some time catching up. But I'm going to try to keep this video as short in time as possible. So number 98. A log equation. Log base 2 of x minus log base 2 of 5 equals 1. These two logarithms are being subtracted, which means that I can combine them into one logarithm where the answers are being divided. Now that I have a single logarithm on one side and an answer on the other side, I am finally in a good position to where I'm stuck. But what do I do when I'm stuck? Well, I change forms. My base is 2, right? Comes from this guy. That's the base. My exponent is 1. That comes from this guy right here. My answer is x over 5, which comes from this guy. From here, 2 to the first is really just 2, and that equals x over 5, so x equals 10. And that's it. Okay, let me go and turn the page, and I'll be back. Okay, we are on the trig identities portion now. Hopefully you guys got the announcement that I sent out on my Connect that said that the first 2 pages of the identities portion is actually no longer necessary for you guys to work on. It's really just the worksheet that has 20 identities on it. It's not the one that has like the 83 identities. That's not the one that I want you guys to focus on. I want you guys to focus on the one that has only the 20 on it. So we will be doing that for the midterm, which, by the way, is your final for trig. So let's take a look at this. Now remember, with trig identities, I already know, and you should already know, that one side equals the other. Your mission is to demonstrate this using sufficient work. So I'll go and flip a coin. Heads goes on the right side, heads goes on the left side, tails goes on the right side. I'll go and flip a coin. Looks like on my cool cell phone app here, looks like tails never fails. We're working with the right side. Okay. So if we choose to work with the right side, in this case, I decided to go very arbitrary on this one because in this particular scenario, either side is actually equally complicated. Normally on a trig identity, you want to choose the more complicated side, but in this number 10, they're both equally complicated, so we flipped a coin for it. So anyway, when you see this, there is no other way around this. You have to use a conjugate. Now remember, these trig identities, you want them to, they want you to practice several things. You're probably going to be tested on like common denominator, factoring, foiling, or conjugates. This one is clearly a conjugate one. These guys will conjugate out. I'm going to go 1 minus sine squared theta on the bottom. And again, I'm not going to be overly aggressive with the top, and I'm going to go and leave it as cos theta times 1 minus sine theta. Okay, and that equals this left side. Well, 1 minus sine squared theta is cos squared theta via a Pythagorean identity. And that gives me cos theta up top, 1 minus sine theta here. Again, since I have 2 terms being multiplied, I can go and cancel those out. I end up with 1 minus sine theta over cos theta. And that equals, still, this left side. From here, I'm going to do a type of separation that we're not normally used to seeing, but because I have a numerator with 2 terms in it, I can go ahead and separate those terms out and put them each over their own denominator, which is the same denominator. And then from here, it closes out. 1 over cosine is secant, and sine over cosine is tangent. And that's exactly what I was trying to prove from the beginning. And there you have it. That is a trig identity for you. Let me go and get the next problem set up real quick. I'll be back. Alright, so number 11 from the law of sines and law of cosines. So with this problem here, first of all, we're going to have to end up using a law of sines or law of cosines on it. Alright, and so it looks like based on the information that we're being given, we have this angle here, 70, with two sides locked in between. So this clearly looks like a law of cosines problem. Again, reason being, I do not have a known side opposite of a known angle. Alright, so my law of cosines dictates me to use some variant of this formula. Whoa, that's not what I wanted to do, right here. C squared equals A squared plus B squared minus 2AB cos C. Some variant of that, okay? So let's read this problem. Surveying. Bill and Joe live on opposite sides of the lake. A surveyor is trying to determine the distances between the houses. The surveyor goes to a point 50 feet from Bill's house and 70 feet from Joe's house, determines the angles in between the two houses to be 70 degrees. What is the distance between the two houses? So that's what I want right there. I'll go and call that C. So here's what I have. C squared, that's the side that I'm solving for, so C squared is equal to A squared. Well, it doesn't really matter which one I choose. I'm going to go and go 70 squared plus 50 squared minus 250 70 cosine of 70 degrees. Now, we're solving for an angle this time, so what you want to do is you want to set your calculator to degree mode. Okay, I'm going to go ahead and do this on my trusty TI-83 here, so you guys can't see me doing the computation, but I will go ahead and simplify all of these in just a second. I don't want to waste your guys' time, so I will pause again. So here's what we have so far, and I realized halfway through the computation that I want to warn you guys of something. So it looks like we've got C squared equaling 7,400, that's what happens when I combine those guys, minus 7,000 cos 70. Now, it's very tempting to subtract these guys, but you don't want to do that. That would be wrong. That's against order of operations. So what you want to do is you want to take 7,000 times cosine of 70 degrees, and what that gives to you is it gives to you 2394.141003. And then you want to take 7,400 minus that answer. And so what you get is you get 5,005.858997 equaling C squared, and ultimately you just take the square root of that answer and you get C to equal 70.752 feet. Okay, so again, the biggest thing I want you guys to pay attention to, one, is understanding your law of cosines, but also I'd like you guys to remember, please do not combine those guys too early. That would not be a good idea. So please don't do that. Alright? Cool. We have one problem left to go, and it is a graph. So in addition to the final review packet, I also uploaded the trig graphs worksheet from a while ago, and please understand that one of these will most definitely show up on the midterm, which is, by the way, the final for trig. And so we'll go and take a look at number 9. So what I've got here is I've got y equals negative 10 sine, oh, no, sorry, that's totally incorrect. It's negative 10 plus 20 sine pi over 3 times x minus 1. Okay, so a couple things to identify first. The vertical shift is -10. The amplitude is 20. I'm also right side up because my amplitude, or the number in front of the amplitude is positive. My period is going to be 2 pi divided by pi over 3, which is going to be 2 pi times 3 over pi. Those are going to knock out, giving me 6. So my new period is 6. And my phase shift is +1. So let's go ahead and take care of this rather quickly. Again, you're going to be asked to graph at least one period, right? And some negative values, just like we've always been doing. Okay, so actually, you know what? Let me go and restructure that. My vertical shift is -10. So I'll probably make this a little bit larger. Okay, so my vertical shift is -10. So that's -10 right there. My lower bound, since my amplitude is 20, my lower bound is going to be -30. My upper bound is going to be +10. Now from here, I'm going to go ahead and just graph sine normally. So sine is normally going to do this pattern here. It's going to go up, and then down, and then up. And also there would be a point that does that. Oops, don't want it there. I want it here, and I want it here. Again, this is my pre-phase shifted graph here. Normally this sine has a period of 6, so it ends at 6 here. This becomes 3. This portion becomes 1.5. This portion becomes 4.5. This tick mark here is -1.5, and this is -3. So again, I have at least 2 values. I'm good so far. Here we go. Let's go ahead and do this next one in red. So it looks like here I'm being phase shifted to the right by 1. So it looks like I'm going to have to create some new points here. The distance between 0 and 1.5, and I want to create a distance of 1, looks like I'm going to go about 2/3 of the way. So I'm going to go ahead and go to here, and this becomes 1. My point was originally here at this 0, now it's here at 1. 1.5 advances over 2/3 again to get me to 2.5. 3 gets me to 4. 4.5 gets me to 5.5, and then 6 gets me to, I'll just scroll over a little bit, 6 gets me to 7. I made a mistake, sorry. That 5.5 point is supposed to be down there, so I'm going to erase this. And then this -1.5 will be at -1, or sorry, -0.5. And this -3 will be at -2. So from here, I just go ahead and graph everything after it's been phase shifted. And there you have it. That's your phase shifted sine. Okay, that is one from each section, so hopefully this clarifies some questions you guys may have. We'll see you guys when I get back.